we have a rigid insulated, there's a typo here, that should have an in there, rigid insulated container fitted with a paddle wheel. It contains 5 pounds of water. Initially, it's at a temperature of 260 degrees Fahrenheit, and it's got a quality of 60%. This water is going to be stirred until the temperature is 250 degrees Fahrenheit. Now, for the water, we want to find the work in British thermal units, and then we want to find the amount of entropy produced, and units for that should be BTU per degree Rankine. Now first, let's point out that this is rigid and it's insulated. Those will be important. Notice also we have this quality that tells you have a liquid vapor mixture at that point. Let's draw a little diagram here. So this is a TV diagram. At state 1, let's just say we are right here. And then at state 2, let's just say we're going to come up to here. Alright, so we're in here because we have a quality, so we've got to be inside that vapor dome. Once we get out here, notice that temperature there is 350. So let's just say it's outside of that dome. Alright, now we've got that. Now what we're trying to do, we want to find work. For work, we're always going to go to that energy balance equation. So same energy balance equation we've been using all of this time. Those two go away. Remember, this is a capital U. We need to switch it over to be able to use specific internal energy. So let's go ahead and notice we can also get rid of Q here because it was insulated, right? So now, if you do that, you'll get W equals negative M times U2 minus U1. So this is switching over internal energy to specific internal energy. Also, I want to point out one more thing. I don't think I mentioned it over here. I drew a vertical line because it says it's a rigid container. So that means volume is going to stay the same. So that's why I just drew a straight line up. Alright, can't remember if I told you all that before or not. Now we've got this, so we need to be able to find U2 and U1. We already know mass. Mass is going to be constant here because this is a fixed volume container actually. So let's go ahead and look for our values. For U1, let's look at that first. Remember, you're given this quality. So for U1, we're going to have U1 equals 1 minus X1 times VF1 plus X1 times VG1. Nope, not V. These are U's. Sorry about that, guys. Alright, so those are U's. We can just plug in these values. These two here are going to come from the table. Alright, we were given our temperature, so you can go ahead and find those values from the saturated liquid table. Now if you plug those in, you're going to have 1 minus X, so that's 0.4. And then UF here is going to be 228.6. And then you're going to have plus 0.6 times UG, which is 1090.5. And units for these things are going to be BTU per pound. So that's going to give you 745.74 BTU per pound. That's your specific internal energy at state 1. Now, while you're in that table, you could go ahead and find the entropy because we're going to need that for B. So I'm going to go ahead and write it down. You're going to have this same equation, except for instead of U, you're going to have S. So again, you'll have 1 minus 0.6 times 0.3819 plus 0.6 times 1.6864. And then that's going to be 1.1646 units or BTU per pound degree Rankine. Alright, so now we've got that, and see, what else do we need to do? That takes care of state 1 conditions. Now we gotta look at state 2. So let's go ahead and look at that. State 2, we know the temperature is 350. You can use the temperature to find your values then. So with this is going to be superheated vapor. So now here, just look up the U2 value in the table. That's going to be 1120.32 BTU per pound. And your entropy value, because we're going to need that, is going to be 1.6699 BTU per pound degree Rankine. Now that we've got these U values right here, we can go ahead and go to this equation 1. And plug that in. So work is going to be -5 pounds times the 1120.32 minus 745.74. That's BTU per pound, which that's going to give us -1872.9 BTU. That's our work. Again, this is negative. That makes sense because we've got this paddle wheel that's spinning. Something's got to power that paddle wheel. The system itself is not causing that motion, so negative makes sense because we've got energy transferred in to the system. Now B, we want to find the amount of entropy produced. So this one, we're going to have our entropy balance equation. So we'll have delta S equals this integral right here plus the sigma. Now this term goes away. Don't have anything for that. That's going to leave us with sigma equals delta S. Remember, this is capital S. That is equivalent to m times little s2 minus little s1. These two values are the ones we found in the table. Now just plug in your mass, 5 pounds, and then plug in these S values. So 1.6699 minus 1.1646, that's BTU per pound degree Rankine. So finally, the amount of entropy produced, that's that sigma term. So go ahead and solve, you get 2.5265 BTU per pound, or per degree Rankine. Sorry about that. Pounds goes away. All right, so there you go.